Okay, good. Slight hiccup regarding the time zones. But I'm glad that a few of you still came back to hear me speak, and also many thanks for inviting me to be part of the seminar series. It's really great to hear this summary of YASA and its mission from you. I don't think anybody else was so well informed about what YASA's history in the past. I had the pleasure of an external researcher to speak to and be so eloquently talking about the history. Because usually, especially in the field of earth sciences, YASA is not that well known. They are very well known for their work on scenarios, climate scenarios. But apart from that, um, especially in the physics or the earth science, that's also my background. Um, People always confuse it with ISTA, which is another institute here in Vienna. So that is really great to hear. I actually also prepared a slide on YASA, but I think your summary was way more comprehensive. I'll put it up nevertheless so that you get a good view of the castle. This is it. It's an old Habsburg castle where the Princess Elizabeth spent a few summers, and then it's our pleasure to now call it the location for which we do this research. It's not the only building that the ASA has. I must add our building where our program is located, the environmental climate and uh, uh, program is located in a more like 70s kind of concrete building, which is not as romantic or beautiful as this one. Um, but apart from that, I can only reiterate that it's a wonderful place to work at, and again, this summer students program is also quite fantastic. We get about 30 something students to join us every summer for about 3 months to work on specific programs, projects with scientists at YASA. Students are usually in their PhD years, early PhDs, and also go through a very nice program and leave YASA very well connected with a really nice overview regarding all things environmental systems modeling. So I can only encourage everyone to have a look at this and maybe join us in one of the coming years as a YSST student. So my talk today will be about accelerating heatwave trends and physical drivers. I will speak about 30 minutes or so, and then I'm sure there'll be time for further questions. And if you have questions about this specific program, then we can also discuss these things. So I want to start with this particular figure that is taken from the last IPCC report, the AR6, and it shows how climate averages, the average temperatures and average precipitation patterns can differ substantially in the trends compared to the extremes. And while the IPCC concludes that temperature changes do not differ much in patterns comparing the average and the extreme, pointing towards the stark differences in precipitation patterns. We can see that, for instance, the drying trend in the Mediterranean happens At the same time as slightly positive trends in extreme precipitation events. I would argue that while the overall sign of change is certainly the same, like we see a shift towards positive values for the average and the extreme, there are still these areas where the trends in the hottest temperatures really outpace those in the more moderate ones. And this is exactly what caught our attention, and um, we looked into this in particular because of this ongoing discussion of an increase of these record-shattering extremes, these types of extremes that are really beyond anything that was observed in a specific region. Think of the Pacific Northwest Heatwave, for instance, in 2021, which really shattered prior temperature records by multiple degrees, really extraordinary in its magnitude, and was one of these first 5 sigma events that were observed in the summer. So a few studies have picked up on this, including this one from Huntingford et al., who looked at this particular trend by calculating the ratios between the hottest temperatures and the average temperature. So in this figure, everything that is above 1, all the areas that have values above 1 are those where the extremes show an accelerating trend compared to the average. And this is particularly pronounced here in this area around Europe. So Europe and the Mediterranean in particular show a very strong signal here. So what can cause these types of trends? So why is the hottest portion of a temperature distribution getting hotter compared to the average? From a statistical point of view, these changes can be explained through changes in the skewness and the variability. So essentially, changing of shape of the distribution by getting more asymmetric, uh, a stronger leaning towards warmer temperatures, and also a widening of the distribution. So a preference of colder and hotter temperatures. And both of these signatures are likely caused by different physical processes. In this nice analysis, McKinnon and others looked at this uh, from a very rigorous statistical point of view, and note the point in time when this was published. This was in 2016, so this didn't even include the last 10 years or so, which are the foundation of the paper by Huntingford and others. But still, you could see in this area, in particular here, where temperatures seem to have increased faster compared to other areas in the mid-latitudes, that there is a positive contribution from these particular features regarding the overall shape of temperature probabilities. So the skewness and the variability show positive contributions there. In our paper that we published just recently, we really try to assess trends in the most extreme events. And we did so with a fairly simple metric, and yeah, a value, a variable that we called tail widening. We proceeded by looking at error 5 reanalysis data and a couple of other globally gridded data sets from JRA, based data sets like EOPS, and calculated the difference between the 87th 0.5th percentile and the 99th percentile, which really related to the hottest temperatures observed within a year, and then did so for each grid point in this particular data set. So you can see this kind of cartoon depiction of what we actually looked at. So we had the 99th percentile for each grid point, the summertime temperatures, or GX, and the 87th. And then we built this particular difference. And if you proceed to do this on a global scale, there are indeed a few areas that exhibit positive values here. Again, this trend is most dominant in Western Europe, but we do also see other areas here in the mid-latitudes, in Patagonia here, or in southern Australia on the high latitudes of North America. Most interestingly, we find that when comparing these trends to climate model output, so the commonly used CMAP6 experiments, models really struggle to reproduce these particular trends. So in this figure here, we depict the percent of models that are able to reproduce or that no, it's the location basically where the observed trend places itself in the percentile of all model realizations. So if we are seeing trends with a number beyond 100, that means that the models do not manage to reproduce the observed trends. So in other words, the observations are outside of what the models projected over historical time periods. And this may become a bit more visual through these box plots, where different types of model experiments are shown here in a statistical way, and then different reanalysis observational data sets are provided side by side, and averaged over these large areas, there are really just a few models that are able to match the observations. And on a grid point level, the observations are really outside of what is modeled. So overall, looking at global statistics of this metric, one must say that models are actually doing fairly well in reproducing more moderate types of extremes. So this figure here provides a histogram of different trend magnitudes, and compares these globally for each grid point. So and again, this is the tail widening, not the temperature trends itself. This is really a depiction of a global aggregation of a metric that measures the difference between the hottest temperatures and the more moderate temperatures. So not average temperatures, but still extreme, but less extreme temperatures. And a divergence of these two frameworks or climate models and ERA 5 really becomes strongest in this area here. So for trends that are beyond 0.5 degrees per decade. And yeah, looking at all grid points, we do see that this signal is strongest also for positive trends. I should have mentioned that if you have questions, then feel free to just speak up. I believe we do have enough time to also make sure that I mention all information that is needed to follow this presentation. So unfortunately, I cannot see the screen and also not the chat. But if you just cough or speak up, then I'll stop and we can just quickly clarify any type of um, uh, yeah, questions you may have. Um, so yeah, the question then is what is a reason for this? Like where do these biases possibly come from? Um, so models seem to be fine with more moderate temperatures, but the most extreme ones, they are really underestimated. And of course, that has implications for um, climate risk assessments that really rely on these CMIP6 simulations as the most comprehensive simulation that investigates future climate scenarios, right? So it is of high interest to understand what's going on there to fill these gaps and possibly adjust them either through kind of post-processing the data with bias adjustment methods or through improving the models from the start to make sure that certain physics are accurately reproduced. Um, so um, this figure, which is from a paper in preparation, um, makes that case fairly clearly. Here we do look at increasingly extreme temperature percentiles. So the more we go to the left, the more extreme the temperature trends that we include in the averaging become. And going up here to the upper left corner, the spatial aggregation gets more precise and precise until we are at a one by one resolution. And comparing observations with CMIP5 exposes these very strong trends at high resolutions that are most underestimated. So it is essentially exactly that scale where we want to have fairly accurate information for a lot of assessments. One by one grid is not even enough, right? It barely hits the city scale. So nevertheless, this figure is an indicator for what we are seeing essentially uh, in observations currently. So very extreme temperatures in specific regions show these amplified trends, and these specific trends are not picked up by climate models. So reasons for this, of course, can be found at different scales, from the planetary scale to the very local scale, from the multi-annual to daily to hourly scale. But as we're dealing with specific feedbacks and very extreme temperatures, this figure here seems to suggest that these smaller scale processes may be responsible for this. So specific atmosphere dynamical patterns that could be underestimated, or certain feedbacks that only come into play after certain threshold exceedances. So one candidate, of course, being soil moisture interactions with atmosphere dynamical features and the amplification of heat extremes. One of the ingredients needed to produce the most extreme heat waves, really. Um, so models could be missing natural variability, and there are a few papers that suggest that. But one big candidate are diverging and underestimated trends and their drivers. And there were a few papers recently that showed that specifically for Western Europe, atmosphere dynamical features from underestimated jet stream trends could really be responsible for these underestimated heat wave magnitudes. Other papers highlighted that humidity trends do diverge, so relative humidity trends could closely be related to soil moisture values, which are then important for these feedbacks and interactions. And of course, for heat waves, aerosols and their trends play a big role, either through cloud formation or through direct shielding of incoming solar radiation. And of course, in models, these are linked to the types of scenarios that we investigate, and it's quite a big challenge to accurately implement aerosol changes in models. So Schumacher et al. Showed that this also contributed to underestimated heatwave trends in Europe. Another important, very similar effect, but slightly different effect, are the responses to surface extremes to particular circulation patterns. So patterns that we know from observations are very strongly related to heat waves, but in models seem to lack that linkage. And finally, and this is from a paper that we published 2022 on the Pacific Northwest heat wave, an underestimation of these interactions, these three-way interactions that were observed to have magnified or amplified the Pacific Northwest heat wave in 2021. And these are the two aspects that I will look into in the coming slides. So first, underestimated trends in circulation, and then these nonlinear feedbacks and the changes in the interaction between temperature, soil moisture, and atmospheric pressure that could possibly be the reason for these underestimations in CMAP6. So one of the most dominant trends in our responses to global warming when investigating atmospheric circulation trends is this weakening of the Northern Hemisphere summer circulation. This is from a paper by Dim Kaumo and colleagues from 2015 who showed that the zonal wind in the mid-latitudes has steadily decreased over the past decades. And together with the zonal winds, also the eddy kinetic energy, so the storm track activity, had shown significant negative trends. And this particular development is also directly related to an increase of specific persistent weather patterns and temperature extremes. So maybe not so intuitive here, but everything that's blue is linked to a negative correlation, which means that a weakening zonal wind, weakening eddy kinetic energy is associated with warmer temperatures. And you can see that here in the direction of the storm tracks, zonal winds that are shown here as contours specifically Europe and Eurasia, but also the East Coast, are affected by these trends. So the 90th percentile, which is associated with the most extreme temperatures, is also strongest affected by this decrease of eddy kinetic energy. And yeah, eddy kinetic energy is very strongly linked to a more persistent summer circulation. The authors in that other paper, they looked at the trends from a more traditional way. In this paper, we tried to follow up from that analysis by really tracking individual temperature patterns. So we used the cyclone tracking algorithm TRACS from Kevin Hodges and adapted it in a way to really track and pin down individual temperature anomaly patterns. And that looks like that in praxis. You can see how the features are identified and followed around the Northern Hemisphere. And the beauty of this approach really is that you can assign dynamical attributes to something that is usually just studied in a static way. But it's perfect to really analyze temperature persistence as you essentially get a velocity out of this quantification. And possibly not surprisingly, we find that weak zonal winds are very strongly linked to temperature persistence. And this is also shown when looking at the most extreme European temperature events in the past decade. So 2003 heat wave, still one of the hottest events historically that occurred in Europe, and the Russian heat wave of 2010 show up as being very slow moving events with very hot temperatures. So often the hottest temperatures are also the most slow moving ones, the most persistent ones. So with this analysis, we managed to make the direct connection between the proposed slowdown of the summertime circulation and stronger temperature persistence, and also the tendency towards hotter extremes when temperature anomalies move very slowly. In another analysis that was published in 2022, we investigated Eurasian zonal wind patterns, so averaged them over the longitudes from Western Europe to Eastern Siberia, and analyzed them using a self-organizing map approach. In this approach, we found three different patterns, and one pattern that we called a double jet pattern. So pattern that is dominated by this strong subtropical jet and this polar branch further up north. And we found that this particular pattern showed an increase in persistence over the past years, and is also associated with very weak winds in the mid-latitude. So a circulation pattern like that also favors stagnant weather in areas around Western Europe and the whole Eurasian continent. And perhaps not surprisingly, there's a very strong relation of this particular pattern, possibly due to its low wind signature here and extreme temperatures in these areas. Um, so um, again, these low winds are also linked to very low eddy kinetic energy here. And we know from the past analysis that these situations favor extreme temperatures. So how do models perform in this particular metric? Um, for this, we replicated the analysis by Rousi et al., who showed the relevance of this double jet pattern for the first time, and also applied the method to CMAP6 model output, um, and found that the anomalies, so when comparing error 5 and CMAP6, were actually quite a good match. So except for a couple uh, biases in the jet strength of the polar jet, one could say that the pattern overall was quite well reproduced. Also not shown here, but the statistics of double jet patterns um, were quite close to the observations. But when we looked at the relationship of these patterns to local heat extremes, that link was completely missing. Um, so that um, gave us basically a piece to the puzzle, but not necessarily the full answer. We still weren't sure what exactly the reason was for why these circulation patterns that were, yeah, fairly well reproduced did not lead to the same magnitude of surface extremes as we observed over the historical time period. So um, that led us to another hypothesis from an analysis also published in 2022, where we investigated this extraordinary heat extreme in the Pacific Northwest. And I talked about this quite a bit already, but here you can see the time series and the anomaly of this particular event to really show how extraordinary it was, right? So there was a positive trend over the past couple of decades, but this one event really shattered all prior records and completely shifted the estimate of return times provided from a GEV analysis. So it kind of broke down this approach as including the event and excluding it completely changes the estimates. So another study from the World Weather Attribution Project called it an event that was essentially like virtually impossible to actually have occurred. So, what was the actual reason for it? So, a lot of really nice papers have been written about this event already that have different um, or like that make different points. In our analysis, we try to investigate the interaction between soil moisture patterns and potential height anomalies. So these two variables that explain quite a lot of temperature variability in the mid latitudes in particular. And in this paper, we hypothesized that during this single event, we witnessed essentially a three-way interaction between geopotential heights, soil moisture, and the temperature itself. So um, the dependent structure of all other heat events is shown here as little dots, as fairly linear. But during this event, that is shown here as diamonds, um, uh, the the relationship really diverged from this linear slope that was found for all other events. So our hypothesis was that there was really an nonlinear interaction of common drivers that occurred during that particular event. Um, and to generalize this hypothesis, we trained um, a machine learning model that took geopotential heights and soil moisture levels as predictors, and also included an interactive term that allowed these two variables to interact, and trained it on heat waves around the globe. And here I show the model performance for one particular event, the 2022 Central European heat wave, an event for which this model worked particularly well. So our aim was to really model these heat wave peaks. And you can see the gray area here that is included in the training data. We identify a heat wave peak, look at the heat wave event and the heat wave period, and include then these time steps in the training to really focus the model on these extreme heat events. And in this case, we find that uh, the model is performing quite well. So it's disaggregating, decomposing the total magnitude into these three components. Um, sorry?
Oh, sorry. No, we just had some students passing. Don't worry. Please
Ah, okay.
continue. But
All
try
right.
to wrap up in next few minutes so we have question time.
Yes. This is my last couple of slides. Yeah. Um, so for this particular event, we find an approximate value of 13% that can be assigned to this interaction term. And we did this on a global scale and found that for the top 10% heat waves, um, the the interaction or the component of the interaction varies between 2 to 14% really. So geopotential height and soil moisture are still the most important variables, most important ingredients to cause a heat wave, but this extra 10% that may lead to a record-shattering event is an interactive term between these two variables. And interestingly, this interaction becomes increasingly relevant the hotter the heat wave gets. So across all heat waves, um, if we analyze the interaction contribution, we find a critical value beyond which the interaction becomes an important factor. Um, and of course, this can also be done in climate models, this type of analysis. And maybe one piece to the puzzle is that this interaction term does not really play a big role in climate models. So while in era 5, this contribution really increases quite steeply with the temperature anomaly, CMIP6 models or other large ensembles do show this relationship, but at a way weaker level. So this could be another reason for why climate models underestimate these extreme heat wave trends. And if you recall the map from the beginning, the regions that we find to be most strongly connected to this interaction are also those that we identify here to some degree as those where models underestimate these trends. So I want to close that atmospheric circulation is very strongly responsible for the observed increase in amplified heatwave trends, leading to several global hotspots, and that models struggle with the representation of these types of trends, partly due to an underestimation of the surface response from circulation patterns that are otherwise quite well reproduced, and possibly as an additional factor or an explanation for that, a lack of sufficient interactions between soil moistures, geopotential height, and additional
Wonderful.
point. Sorry?
No, sorry, no, sorry. I thought you were finished. No, go ahead, please.
Yeah, now I'm finished. Thanks a lot. Thanks a lot for listening. I hope this was more or less clear, but we do have some time for questions. So looking forward to discussing this and also hearing your ideas.
Great, wonderful. Thank you so much, Kai. Let's open it up to Q&A. And since we're a small group, I think it would be nice actually if we can have introductions as well quickly if people, when they ask a question. In particular, I should note Aarti Arora is our graduate student, PhD student who recommended you for this seminar. So Aarti, would you like to say a few words, introduce yourself?
Hi. We've met previously. I took your complex climate risk class, and I thought that
Hi.
it would be cool for you to come talk. I'm
Awesome.
a
Yeah, nice.
I'm a PhD student, second year in Kyle Davis's lab, but I'm working on agriculture sustainability.
Yeah, great to meet again, Nati. Thanks for pitching me to speak at the seminar series. I hope everything's going well in Delaware.
Yes, and you too.
Yeah, nice.
Great. Thank you. And we also have two faculty members here. We have from our climatology program, Dr. Shuai Wang, who works on hurricanes and cyclones and extreme events. And we also have Professor Pablo Huck from our School of Marine Science and Policy, who's in the room with me here. And he does ocean-related research. I'm not quite sure exactly how you define yourself.
Yes. Hello, a wonderful talk. My research is on turbulent transport of heat and momentum, water vapor. In some ways, it's at a smaller scale than the scales we talked about today.
Yeah, great meeting you. Thanks for being here.
So, any questions, Shuai? Would you like to introduce yourself too?
Yes, sure. Hi, Kai. I'm Shuai. I'm assistant
Hi.
professor working on extreme weathers. So I can definitely see we share some research interest, but mine is mainly over the ocean, which is completely blank in all your analysis. Yes, I
Yeah,
focus on hurricanes, and also the impact for the coastal regions. Thank you very much for the excellent
cool.
talk.
Great meeting you. Yeah, thanks a lot.
Any questions?
Yes, actually, I have a few questions, but I'll keep it short. So, I think it's very interesting, like the analysis for the hotspots, like you show here. When I think about hotspots, so there are like two hypotheses. One is the local forcing is too strong, and then the response actually roughly the same, and mainly due to the local forcing, then you have the hotspots. And another hypothesis is like large scale forcing is roughly uniform, and then just because some regions we just have a very strong feedback, and then that's why we see these hotspots. So I just want to ask, which one do you think is more important? We do when we look at these regions showing the hotspots.
I think overall models are actually warmer than what we see in observations, right? So this is not showing here because we remove basically that signal and really just look at these relative changes. So I would argue for the second option that you proposed here, that it's not necessarily the large scale forcing, but really like regional feedbacks. And I have to mention also that this paper back then is more of a phenomenological one where we highlight the differences, but they can really be due to a lot of different reasons, including natural variability to some degree. I think that's important to mention. And and also I think again like models are actually quite good at reproducing extremes at larger scales. It's really almost at the grid point level or below where it becomes um, maybe a bit problematic, and also only for these very extreme trends. So this just in the defense of climate models, they actually do fairly well. But unfortunately, these extremely or these very extreme events are those that are often associated with the strongest impact. So we thought it would be important to make that case and to maybe also highlight a couple of areas that deserve a bit more attention. So in my talk, as you might have seen, I looked a lot into Western Europe, and that's unfortunately, or maybe fortunately, that's where I'm located right now. So there's a lot of research on this area from my network, let's say. But I would really like to see other groups, or maybe we also get a chance to do this at some point, to look into all the other regions that we point out here, and maybe also manage to align this map with other metrics like this one in the ratio metric. A couple of regions agree, others disagree. Overall, the patterns seem to be a bit larger and less patchy. Um, yeah, so there's still a lot to look into, I hope, and certainly not the last word on this.
Thank you.
Thank you. And Pablo, you had a question.
Kai, is the density of data over the oceans, presumably it's less than the density of data over land. So I was wondering, is the heat flux to and into the oceans robustly accounted for in the different models?
That is a good question. I have to say that I'm not entirely sure. This was not part of our analysis, so you have seen that the study is really focused on land area where we thought these feedbacks to be strongest. I would say, like intuitively, that well, apart from these long-term trends in the Pacific that seem to diverge in models and observations, overall the extremes are probably a bit better reproduced as the variability is not as strong over oceans compared to land. So maybe these peaks are just a bit more damped. But I would not dare to make any strong statements on this, and yeah, maybe others in this call have more information about that. This study was only focused on land area. But yeah, there's a lot of interest in ocean heat waves as well. So maybe it's worthwhile to repeat this and look into trends and biases of sea surface temperatures and then the extremes. So short answer, I don't really know. I'm sorry.
Thank you.
Well, there's a window for land-sea cooperation, maybe more research. So, excellent. Ashley, please.
Hi, Dr. Kornhuber. I'm a first year climatology PhD student. My research is on the the summertime circumglobal teleconnection, and the
Cool.
link between that and US heat waves and connecting that to Rossby wave packets. So I know you kind of mentioned the three-way interaction between geopotential, temperature, um, and soil
Mhm.
moisture. I kind of was just wondering, or just to hear kind of any of your thoughts on specifically the summertime circumglobal teleconnection and how possibly like a strong CGT event, for example, could maybe precondition the land, and if there's maybe any relationship between biases in the representation of the circumglobal teleconnection and soil moisture biases, specifically in the US that you might know of, or in Europe as well.
Yeah, I think that relationship is very important for these types of teleconnection. So might depend a bit on the type of time scale you look at. So if you look at seasonal patterns, maybe other more slowly varying components becoming more important. But there are a few papers um, by and Teng and Brandstetter that really emphasize the importance of soil moisture to um, initiate these patterns to some degree or serve as an anchor point uh, and can really trigger these waves on a global scale. So a couple of really nice modeling studies and then of course looking at individual heat waves, soil moisture is always one of the driving factors in the mid latitude. So there's certainly this a very strong connection that points almost in all directions as a driver, but also as a, of course, something that is strongly affected by um, one of these circumglobal wave patterns. And yeah, there are a few papers on the way that I know of that also make the case for model biases and this relationship. Uh, I think I'm not sure if it's out yet, but I could quickly Google and put it in the chat maybe. It's by Chai Hong. I'll send to you later.
Thank
But
you.
yeah, I was at a conference not too long ago where many people focused on this interaction. So it's certainly something to look into. I'm not sure if you work with models or observations, but in both cases, that would be really interesting.
Yeah, awesome. Thank you so much.
Great, thank you, Ashley. Numan, you had raised your hand.
Hi, yes, I had actually a question also. Can you hear me?
Yes.
Yes.
So, hi, I'm actually a final year PhD student, and I'm also interested in working in the extreme weather events. In fact, my research work is about atmospheric rivers in the northeast of the United States. So, while I mainly work with the machine learning techniques to identify any distinct patterns or the long-term patterns in this region. So I don't work directly with the CMAP models, but of course I come across various studies or the results of those studies. So I was kind of curious, like, do you have any advice for someone to like, if someone is new to that field, how one can work with the CMAP models? Or general advice for the students, are they available as a open source and where to start, especially for looking at regional studies, for example, a specific region like Western Europe or maybe the Northeast of the United States, etc.
Yeah, they are freely available. It's sometimes these data portals are a bit difficult to use, but you should be able to find them fairly quickly, and there might even be libraries out there now through Pangeo and other nice tools that allow you to work on these data sets through, yeah, like Python and cloud techniques. But yeah, this is all available, and yeah, you may even want a larger database to look at. Then for this, you could probably look at these large ensembles, these CESM large ensembles, to train your models. So I'm sure your colleagues can help you at the university to get that data. But luckily, this is all freely available, also for different scenarios. So I showed results from historical simulations of the past, but these are also available for different pathways into the future.
Does IASA have any resource library or something which is a link you could provide?
So YASA hosts these scenario explorers where I think the input data is provided, or like scenario relevant metrics such as population changes or assumptions about land use change, things like that. I could Google quickly where the CMAP6 data is hosted, but I think there might be different institutions or several institutions that provide it.
Yeah, Numan, I think we should try to make sure our climatology students get these kind of resources easily. Excellent. Well, I think we're at time. We really appreciate you joining. Sorry for this confusion, but we have recorded your talk and it will be online, and we'll spread the word so your presentation gets a wider audience afterwards. And yes, please keep in touch. If you're visiting the Northeast, we are very centrally located, just a train ride from New York or Washington. So right in the middle, just 30 minutes from Philadelphia, 35 minutes. So, all right. Great.
Thank you so much.
All right. Yep. Bye-bye.
Have a great day. Ciao.